Kaushal, will you please confirm that you see the recording on?
Yes, ma'am. Start recording.
And the slides are visible correctly, right? Okay.
Yeah, yes, ma'am.
Thank you. Okay. So, welcome all, and let's recap what we did in the last class. So as we know, we are in this week, we are looking at loops, and in particular the while loop construct. And yesterday we saw at least a couple of tasks which we performed using the while loop, and we saw again we saw that what kind of a loop invariant is maintained in the simple min program that we had written down. We had looked at deciding whether a given number is prime or not. And finally, towards the end of the class, we were looking at this problem, which is computing the GCD of, this is not two programs, of course, two integers, GCD of two integers. Those are given to us, and these are positive integers. So I'm going to spend a little bit of time today again looking at that problem, going to REPL and executing that, because I felt it was a little rush towards the end of the class yesterday. So the first idea that we started with is this simple idea that if we are given two positive integers x and y and we want to compute the GCD, we compute the min of that is z, and then from 1 to z we check whether I is running from 1 to z, we check whether I divides both x and y, and as long as we keep finding this I, we keep refining our update of the GCD. When we hit z, we have exhausted all the things that we could have tested out, and therefore whatever is our I at that stage, we will output that as our current estimate of GCD. So this is a correct algorithm or correct idea, and we could have written this down from z to 1. We said that if you write it down from z to 1, you must break the first time you get the divisor, and that will turn out to be better in some of the cases, but not all, as we will see in the large inputs that we were testing in the last class. Okay, large inputs which were actually prime numbers. Okay, so this is the implementation of that idea, right, using a C program and the while loop construct that we have, and this is what we have seen. So are there any questions or comments about this? Okay, so moving on, we also looked at this idea, very nice idea by Euclid, where it says that if y divides x, and we will assume for the assume throughout our iterations that x is always the greater of the two, or x is no smaller than y. So if y divides x, that is x mod y is equal to 0, or equal to 0 in our language of C, then we are done. Then we simply output y as our GCD. Else we modify x and y suitably, and the suitably is dependent on what is the best way you can think of it. So the one of the ways was just subtract y once, but then we saw that subtracting y once can be done repeatedly, and therefore we said we could have set x is equal to x mod y. Now this next statement is, what if x is less than y? In fact, if you do x is equal to x mod y, then you will have x, the resultant x that you will have will be between 0 and y minus 1. Therefore it is going to be less than y, and therefore you will need to exchange x and y. So this is something that you would have observed if you paid a little bit of attention to this. So if you set x is equal to x mod y, then the value of x is going to be less than y, and therefore you will exchange x and y and repeat this. So yesterday I had shown you a template of this program where you were asked to fill in these things, that is this while loop condition, as well as the modification of x, and then the exchange of x and y, all of which I have written it out here now. So this program is the same as the template that was shown, but the details have been filled out. So we scan X and Y, which is the standard stuff. If X is less than Y, then we want X to be greater than or equal to Y always. Therefore, we swap it. That is, we do this routine procedure. So computing min, computing or swapping two integers is something that we know now very well. So I'm not going to spend time on that. And then as long as X mod Y is not equal to 0, we keep entering the loop. We set X to be equal to X mod Y, and as we agreed that it will set X to be something which is strictly less than Y. Therefore, we are going to exchange the values of X and Y, which is the same code which has been repeated here. And at the end of this, you know that Y contains the GCD because you have exited the while loop, because X mod Y is equal to 0. And therefore, you know that the GCD is contained in Y, therefore you just output Y. So this is the program that you would have possibly attempted to fill in. This is not the only correct way. There are other ways to do this, but yeah, this is one of the ways in which is just implementing this idea that has been written on this slide. So are there questions here?
Can you just go to the previous slide once more?
Can previous slide?
Yes.
So do you mean this one or the next one?
No, on the slide which has the program.
Sure. Okay. Yeah, sorry. Yeah, this one. Okay.
Okay, thank you.
Yeah. Okay. So I'm going to change the view and I'm going to go to repl.it to show you again. All of you are encouraged to do this in your lab or in your free time whenever you get, and try this out on large integers and see the difference of the performance of these programs. So yeah, Kaushal, please tell me whether you will, once you start seeing the repl.it view. Yeah. Okay. So as I said yesterday, I have already written these programs ahead of time. I mean, anyway, they are written there on the slides. I have just copied them here. And we saw this GCD is the simple GCD where it runs from 1 to Z, and it checks whether this I divides both X and Y, in which case you set the GCD appropriately. And of course, increment I. This is important when you are writing a while loop. And the way we compiled this program is we said, just to make sure that we have two executables ready, we'll say GCC, which is the compiler, GCD1.c minus O. I hope you are all familiar with this, GCD1, which is the executable that is created. This is the first program. Now there is one executable or one executable which allows us to compute the GCD. There is also another this is the executable that I have typed out. So therefore you see this garbage here. But there is GCD2.c, which is what we have seen as the program, which is Euclid's idea. And this is the program that I have again typed it out. I'll just compile it as GCC GCD1 GCD2.c minus O GCD2. Right, and so again there is this standard error. I can change that, but doesn't matter. So now you have two executables, GCD1 and GCD2, and we want to check out how they perform. In fact, we did that in the last class. I just want to repeat this. If you do the performance of this, or if you check out on small numbers, they will behave just the same, so you can't see them. So what I have done is I have taken two large inputs, which I have stored them in this file, which is called GCD inputs. These are two large prime numbers that I have pulled out from the internet, and these are illustrative to show that when you run the first program, which is GCD1.c, it is going to go from 1 all the way to the minimum of these two, which is this 961, the first one, and find out that it is none of them is a divisor, and therefore it is going to say that GCD is 1. On the other hand, when you look at this program GCD 2, in fact, if you enable these prints, you will see how quickly the values of x and y are changing. So I'll just recompile the program. And what I'm going to do is run these programs GCD /GCD 1. And in case, I think people may not be familiar with this. This is the input redirections symbol, which saves me from typing out these large numbers. And because these are large, I don't want to make errors in typing them out. So I just give it as an input, and we have seen that it takes about 5 to 7 seconds to compute this. So the answer is correct, of course. However, if you do GCD 2, you will see that rapidly the two inputs x and y are going to go down, and as they go down, number of iterations done is very small. So you can see this program in execution and see the effectiveness of this program on large inputs. So it's not about the program, it is about the idea that is very efficient, and that is why we are seeing this very good and effective performance. Sorry about this. Yeah, so this is what I want you to look at. Okay, so any questions, comments, or anything that you want to ask? Okay, so the class is again unusually very silent. I hope everybody is with the class, and okay.
Can you show
So
us two numbers once again?
sorry, I can't hear you.
Can you show those two prime numbers once again?
The two prime numbers. Yeah, sure. I can show the two prime numbers. I can also put them on the slide if you want them to be given. That is, you can take any two large prime numbers. I mean, as long as they are large enough, you will see this behavior. Doesn't matter. These primes are not very special. It's just any two large primes. Is that okay? Yeah, great. Okay, so I just want to understand. So have people already seen this Euclid's idea earlier? Again, just to get a sense, I know I have repeated it, but I mean, before this class, have you seen it earlier in your, when you studied programming or earlier?
I think we had in like in maths, I think.
You had it in?
Maths, 10th, in 10th, I think so. Like
Okay,
Euclid
okay.
division lemma.
Okay, great. So you have seen this idea, but I mean, at least some of you say that you have seen this earlier, but I'm not sure if this was shown as an illustration or the difference of this was shown during your programming course. And I mean, this is something that tells the power of a good algorithm, as we said yesterday. So this is something which is very illustrative of the power of a good algorithm. So I hope the message that we wanted to send using this example is clear, and the idea may be known to you, but the implementation or the stark difference between the two performances may be something which is surprising or which is also appealing to you. Okay, so with this, I assume that there are no questions about the problem itself. Okay, so I'll just stop sharing the repl.it screen and go back to the slides.
Ma'am,
Yes.
when we find GCD, we had a third method, no, ma'am, where like for GCD of x comma y is equal to GCD of x minus y comma y and so on like that. So can we program it as? I mean, can we do this program?
Sure, you can do the program. But what we are saying is once you have that idea that GCD of x comma y is equal to GCD of x minus y comma y, then this is just a few steps away, right? I mean, you are doing more iterations by saying GCD of x comma y. I mean, you are just doing more iterations and reducing the numbers slowly. Is that clear?
Yes, ma'am.
Yeah. So that also you can try it out and you can see the performance.
Actually, the problem is what should be the while condition, man? Because there,
Okay.
I don't know where to stop, ma'am. Actually, like because x minus y will differ for each, depending on x and y, no, ma'am. As we go.
Mm-hmm.
So what
But
shall
what is okay? So the question for everybody's benefit, I'm just repeating it. So he's having this thing. So while something, do x is equal to x minus y. Is that correct, Kannikeshwar?
Yes, ma'am.
Okay. So the question that he has is, what should be the end condition? Any thoughts or anybody has suggestions on what should be the end condition for such a program? Okay, I see two answers, but okay, a few more. I'll wait for about 30 seconds and then. Okay. Okay, so there are some answers, not many have participated, but fine. So I want to ask Kannikeshwar who has raised this question. So I don't want to give away the answer, but because not many people have participated. But what if you have two numbers, we have taken here positive numbers, but if you have two numbers and one of them is 0, what is the GCD of those two numbers?
It should be 0, no, ma'am.
Okay.
I don't know, ma'am.
Okay, so if you don't know, think about it. What is the GCD
Okay.
of a positive number and 0? And then hopefully it will lead to the answer. Some of you have given the correct answer in the chat messages, which are possibly, yeah, I mean, I'm not saying we are talking. So one of the questions is that is it defined? Do we have what is the GCD of 0 and this thing? So, but okay, so what will you want it to be in this format where you have two numbers where you are just subtracting repeatedly from the other number, right? And you are also maintaining this invariant that x is greater than or equal to y. Is that clear, Kannikeshwar? I mean, in the last slides, I showed this
Yes, ma'am. That is
execution, right? Okay, so for everybody's this thought and this thing, it's a nice question. So if you replace this as x is equal to x minus y, what should be the end condition of this while loop? Can you come up with the modified end condition? Please think about it and write down that, and maybe we will discuss it.
Ma'am, isn't this just that but more efficient because you're repeatedly subtracting y many times and then you're taking the remainder and then swapping and then doing it, right?
Yes, that is exactly what I said as a first answer to
And why
Kannikeshwar.
do
But
we need this?
why
The
do we
second method. What he's
say
suggesting, isn't this better? That's what I'm asking.
which is better? Which
What
one?
you've done.
So that is my response to what I said earlier to Kannikeshwar. The first answer that I gave it to him is saying that if you repeatedly subtract, I mean, you are just going to do that, right? If you as we saw in the last slide, right? If you had, if you could subtract x multiple number of times, you are going to do more number of iterations to just do that. That's what you
Yes,
are
ma'am.
saying, right?
This is
Yes.
just directly taking the remainder, subtracting
Exactly.
as many
So,
times.
but yeah. So, what I think Kannikeshwar's question is simply, what if you write x is equal to x minus y? It is also a correct update rule. There is nothing wrong. do you have to change this, and how do you change this? That is the question. So I'll leave it that as a small exercise for you to do. How do you change the condition if it has to be changed, assuming that x is equal to x minus y? Of course, in this case, it is not always the case that x will be less than y. X will be less than y. So you should check whether x is less than y, and only when x happens to be less than y, you should swap. So there is a small check that you have to do. But other than that, what one of you has pointed. So what is your name? Whoever is speaking, it doesn't show up here. ME20B051, sorry.
Yes, ma'am. Chinmay.
Chinmay. Okay, so Chinmay has said that this is exactly, I mean, this is what we are doing in an efficient way, which is correct. But if you want to implement it, how will you implement it? That is Kanikeshwar's question, and let's try to answer it individually. So I am not going to give away the answer, because that is something that will force you to think about the end conditions and so on. Okay, yeah, so let's, I mean, you are writing messages now, but it's okay. I mean, each one of you can write down and try this out and also argue about its correctness. Okay, so having said that, let's move to the, any other question related to this, or implementation or anything? Okay, so we are going to move to today's task, which is slightly different from the task that we have been doing, but again, something which is useful and which will illustrate a different idea, maybe something that you have seen, but I'm not sure if you have implemented, which is computing these common mathematical functions. So these are provided to us and in the library, standard library. But at some points, if we want to implement these common mathematical functions, we should also be able to think of how we will implement these functions. So we'll start with something which is very, very basic, which is computing the positive square root of a positive integer, right? And we will compute it approximately, right? So we are going to compute this positive square root of an integer approximately, and we are going to see a method, we are going to implement it, and in the lab you are going to do some variant of this, which again will be clearly specified to you. So at this point I want to make a small remark about the expectation and the nature of the assignments and the course. So for example, when we saw the GCD idea, there were two things. That is, one is the standard idea, that is going from 1 to min, and this is the first idea that may come to your mind, and the second is Euclid's idea. Unless you have seen it or you think about it a little bit, you are not going to get it immediately. So when we are in the context of this course is not about designing new algorithms, although that is a very interesting field. But so we are not going to expect you to come up with new ideas here. Most of the ideas you have seen, but we are going to implement them or show variations of that, which will lead to better running times or illustrate some of the programming aspects of it. So in a similar spirit, we are going to see the computation of the square root of a positive integer, the positive square root of an integer. We are going to see an idea, implement it. When you are asked to implement a variant of it in the lab, you will be given the variant and you are supposed to implement it faithfully. So this is the spirit of the course, that we are not going to, most of the times we are not going to invent new ideas here or design new algorithms, but implement what is known to us or teach what we know to the computer via our communication language, which is the C programming language. Okay, so we'll set out with the simplest task of computing the square root of some positive integer. Let's say 102 square root 55 555. Again, these numbers are simply chosen. You can compute the square root of any positive integer that you want. And as I said, we have this time tested SQRT function that the library has made available for us. But we would like to see what could possibly be an implementation. We are not saying that this is the implementation, but we'll study a simple and effective method, which is called the bisection method, which will allow us to approximately compute the square root, and it will also allow us to decide how close we want to go to that approximation of square root 2. Not square root 2, square root of the positive integer, let's say y that we want to compute or x that we want to compute, right? So this is our goal in this task that we have. Okay, so just for the sake of concreteness, let's take 55 again, no specific reason, and let's try to compute the square root of 55. So when we say we are interested in computing the positive square root of 55, we are looking at this function fx is equal to x square minus 55, and we want to find out the value of x where this function evaluates to 0. And since we are interested in the positive square root, we are interested in a positive value at which this function evaluates to 0. So this is our goal. So we want, in fact, fx x squared is minus 55 is equal to 0. This is the fx is x squared minus 55. So to begin with, let's plot this function. So I have just done this using some tool, and this is the function that is plotted. And by just guess, you know that this is going to lie somewhere at 7, I mean 7 point something at the positive square root. So you are aware of this. So we are just coming up with an idea about how to compute this, right? Okay, so so let's say we start with some initial guess and ask, is 1 the value at which it evaluates to 0, right? So let's say we ask this. In fact, if you compute f of 1, we know that it evaluates to something which is negative. Okay, so 1 is somewhere here. So is my pointer visible, whatever I am doing? Can Kaushal or somebody say?
Yes, ma'am.
Yeah, so I mean the ranges are given, so I hope you see that this is 10, 20 and so on. So 1 is somewhere here, the value is negative, and so f of 1 is negative. Now let's choose another guess, or so since it is negative, and so we are going to increase our guess, and let's say we overestimate it, and we actually try to find out a value for which it is positive. Let's say we guess 25. Is 25 the square root of this thing? Again, this may seem again very simplistic, but we want to illustrate this idea of this bisection method. So let's say we guess it to be 25. We compute f of 25 and it happens to be positive. Then since the function is continuous, it must be 0 in between these two values, 1 and 25. So we need to navigate this range, which is 1 somewhere here and 25, which is somewhere here, and we want to compute this compute a possible value. How should we select this select the third one? So we want to refine our guess, right? So we want to refine it. A good way to refine it is possibly select something which is in between x and the left endpoint and the right endpoint. So the computer refined guess, which could have been something else, but we just take the midpoint, and that is why the name comes the bisection method. So now we have 3 values: one which was the initial value, which is 1, the second value, which is this 25 that we had guessed. These are the 2 initial guesses, and then we have a third. So what is the property of these 2 guesses? The two guesses are such that for XL, f of XL evaluates to a negative value, f of XR evaluates to a positive value. These are the two different guesses that we have done. Again, we have called them left and right just as indicative, but these are 2 guesses that we started with. Now, of course, if we are very lucky and if we had guessed something which is the exact square root, these are, of course, this could have been fractional values, and you could have gotten very, very close to 0, either positive or negative, but you could have gotten very, very close to 0, in which case we can stop. But at this moment, our guesses are very far away from what is the square root. So therefore, we guess a third, or we compute a third value, which is the mid of these two, that is XL and XR. And then what should we do? So once we have these three values, XL, XR, and XM, which are the three values, what is the thing that we can do to further refine this process? So in the pictorial sense, you have this, there is XR, which is somewhere here. So this is 10, 20, 25. And the mid value is, of course, going to come on the right hand side. So now what should you do with these three values? How should you refine it? So can people write down?
And
Okay,
we should
again,
always take two values which have opposite sign and find their midpoint, right?
okay, so we want to repeatedly keep our invariant that we have two values, one of which evaluates at one of which f of x evaluate f of the left endpoint evaluates to negative, the right endpoint evaluates to positive. And since we have initially we had XL here as 1, XR here as 25, we now want to change one of them. So what do we want to do? We want to close this gap as much as possible. We started here where the left endpoint was possibly much closer than the right endpoint. We are now going to try to close this gap. Our midpoint happens to be on the right side, so we are going to change our XR and ensure this invariant that XL and XR lie on two sides of that function, that is XL evaluates to negative, f of XL evaluates to negative, f of XR evaluates to positive, and keep doing this, right? So this is exactly what is the template of our algorithm. We start with two initial values, XL and XR, take the mid, and okay, so again, if f of XL or f of XR happens to be 0 or very, very close to 0, you are done, because anyway we are computing it approximately. So you are going to take the so if that happens to be very, very close to 0, you just return that as your output. If not, you take the midpoint of that, which is XM, which is XL plus XR by 2. You compute the value of the function at XM and pick the two of the three values which are closest and have opposite signs for f of x, right? So this is something that many of you have answered in the chat. So depending on what is the sign of f of xm, you are going to either change XL or XR and narrow this gap that is there for the two extreme guesses or two guesses that we have made, XL and XR. And how long should you do this? How long depends on how close you want it to be how close you want it to be the value. Anyway, it's an approximate this thing. So that as long as they are close enough, that is XL minus XR is greater than some error epsilon that you are willing to tolerate, right? So if it is still greater, you keep continuing and refining this guesses and updating your XL or XR based on the midpoint of the two values that you have found out, right? So this kind of methods are called as iterative methods, and it is related to the iterations that we are doing of our loop in either the for loop or the while loop. But this is again again something which is conveniently done using the while loop itself. So what I have done is I have defined again this program is very specific to compute the square root of 55 alone. And why is it 55? Because I have not taken any input from the user. I have just taken this 55 and hard coded it here. So I initialize XL to be 1 and XR to be 25 as I have mentioned, but these two can be taken as initial guesses from the user. Again, the user may give initial guesses which are not valid. Why are they not valid? Because possibly both of them lie on the right side, or both of them lie on the left side, in which case we are not going to use them. So we ask the user to give guesses which are of this nature, where f of xl evaluates to negative, f of xr evaluates to positive, and also an input epsilon. In fact, again, I have hard coded this epsilon here, which is 0.001, but the input epsilon which the user is willing to tolerate, right? This is the error that the user is willing to tolerate. And as long as xr minus xl is greater than or equal to epsilon, as long as this is true, you are going to keep refining your guesses. And this is exactly what we said in the previous slide. xm, that is the midpoint is computed. If the function value evaluates to positive, then you are going to change the estimate for xr, else you are going to change the estimate for xl. And when you have exited out of this while loop, you have that the error between these two is less than or is strictly less than epsilon, in which case you return either one of them, the xl or xr, as your guess or the approximate value for the square root of the input value that was given to you. So this is a hard-coded program for the square root of 55, but you can of course change it to take inputs from the user. The inputs are going to be for what constant you want to find the square root, what are the two initial guesses, and what is the error that you are willing to tolerate. So once you change all of that to be input from the user, you are going to write a small program which will approximately compute the positive square root of a positive integer. Okay, so any questions or comments here? Okay, so I'm just reading the chat messages. Yeah, so the first one I think is, are you taking these two guesses randomly? So as I said, I took them arbitrarily, not randomly, arbitrarily, but in general, you are going to ask the user to give the guesses. Then, okay, so yeah, so this 2.0, right, it is not required because we know that XL and XR themselves. Okay, so the question is that should this division by 2 be 2.0? It doesn't matter. These are already doubles, defined as doubles, so these won't be truncated to, I mean, typecast to integers or something.
Ma'am,
Yes.
ma'am, actually, like if we get input from the user for XL and XR, we need to ask, they need to be aware of the graph, ma'am, because like one value should be less than zero,
Yes.
should be greater than zero. So,
Yes, so the user needs to be aware of the graph. Yeah, I agree.
okay.
Okay, so we can take XL equal to 0 and XR is equal to input plus 1. So what is input? Sridhar has written this. What is input?
Value which the user enters for finding the square root.
Okay, but I mean, okay, so this is okay, so why do you say that it is okay, 0 is fine, or and input plus 1? Sorry, what is input? I missed it.
I mean, the value which the user enters for finding the square root.
55, is it?
Yes.
In this case, 55, right?
Yes.
Okay, yeah, so these can be taken, I mean, these need not be taken by, these need not be 1 and 25 or something. You can also choose, as I said, these can be any two values as long as they have this property that XL is, f of XL is negative, f of XR is positive. But if the user gives you a better guess, you will converge faster, right?
Yes.
Yeah.
So in this
Yeah,
case, the
can't-
user will not give a guess. If
In
the
this
program
case,
if the program itself takes Excel and XR values, user won't have to input a guess. Right?
yes, I agree. So there is also one more this thing, that can't we make the computer do the guess? Yes, the computer can also do the guess for the left and right hand point. But the computer, okay, so there are small caveats to this, but so at the moment I will just leave it that the user gives this guess for you. But yes, you can modify it, and to some extent the user needs to know the graph of the function. Okay, so one of the small tasks that you can do in the lab is also ask yourself, how will you modify the program to get you the negative square root of a given positive integer? Not difficult. You can change some of the things that we have written. You can do it explicitly for this 55, but you can do it for any input that the user gives. So this is all I wanted to say about this example. Also, I want you to observe that we have this loop invariant again, that XL minus XR is it is greater than or equal to epsilon when you enter the loop. XL is a value that is such that f of XL evaluates to a negative value, f of XR evaluates to a positive value, and this invariant remains unchanged by this update rule that we have done, right? So again, the expression gets updated, which is something which is important for our while loop to terminate, which does happen. It also maintains this invariant that we had started with, that XL and XR lie on the two sides of this function. Yeah. So this is a completely different example from the examples that we have seen in the yesterday's class. Illustrates the use of the while loop, and computes an useful function, gives you an insight of how possibly the SQRT function could be implemented. Okay, so yeah. Okay, so there are some questions. I'll answer them, but for the moment I'm just going to stop the recording. I'm done with the class, and I just want to, okay. Yeah, so I'll just make one of these remarks that I wanted to say, that in the yesterday's discussion about the quiz, I had mentioned that we will have whatever we have done in the course till now. So that is true. We did not study this thing about, or we did not look at this construct of continue that is used to again modify control flow in the while loop or in any of the loops. So that is something that is not expected, or that is not in the syllabus of quiz 1. But whatever we have done till today will be a part of quiz 1. Again, I repeat that you are not expected to know these methods or bisection method or something. That is not the goal, but you should understand the underlying implementation aspects of it, how it is implemented, and you should be able to read code or implement it if you are given such a code. Okay, so yeah, that's all for today. We'll meet in the afternoon at 2:30 if we for the lab, right? Okay.